Hello everyone, this is lecture 14. Um, we'll study today the simple linear regression model. Um, Up to now, we studied 2 weeks ago and the week before. We studied the correlation analysis, a relationship, linear relationship between two variables. But at that time, we didn't consider which variable is dependent. The simple linear regression model is considering one variable to be dependent and the other one is to be independent. So you have one dependent and one independent variable, or one dependent response. You can call it response variable. The dependent variable can be called response variable, and the independent variable can be called explanatory variable. The reason why we call it an explanatory variable is that the variable is explaining the response, the reason for the response. And the difference between the simple regression model and the correlation is that the correlation measurement either could be a Pearson measurement or a Spearman measurement. And for the Pearson measurement, Pearson correlation measurement, you need to have two variable to have normal distribution, as a result to be continuous variable. In the simple linear regression model, you have only a single assumption that the dependent variable should have a normal distribution, definitely. But the independent variable or the explanatory variable does not require a normal distribution shape. Okay, so this is the lecture note I copied from the book I was using mostly for this semester lecture. And this is the model assumption I copied for you. It's good, prepared. A simple regression model is a linear equation having a y-intercept and a slope with estimate of these population parameters based on sample data and determined by standard formulas. The model describes in terms of the population parameters as follow. So this is the model we're following. Okay, I'm gonna use the right. That's the simple linear regression model. This is in fact a functional relationship between the dependent. The dependent is yi and an independent xg, and no assumption on the x, and there is a strong assumption requiring the y to have normal distribution. So yi a value of the dependent variable xi, a value of independent variable x, and beta null is the intercept. So in some books, in some lecture notes, you may consider the intercept as constant. You call it as constant. The intercept is also called a constant. Okay. And beta 1 is the slope of the regression line, and no difference. We prefer to call it the slope. Yes, that's fine. And the epsilon I is the random error or the residual. In fact, we don't call it residual. The book is calling residual. The residual is, in fact, the term used for the estimated model. For the population model, this is the population model. We never call it, this is not the model we call the estimated model. It is the population model. Yes, okay, this is the population model. So those items are very useful to understand the idea behind the linear regression model. For a given, the first one is for a given value of x. The expected value of y is given by the linear equation. This is the expected value for a given x. Any value of x, you can calculate the expected value of y. So this is the expected value of y, the mean of y. So I would call it the expected of y. In the book, it's the mean of y given a specific value of x. That's good. The difference between the actual value of y and the expected value of y is the error, but not the residual, because the residual is the actual value and the estimated value. So this is the difference. So I'm gonna fix this for you. This is the error. Okay, I will consider this is the error. That's the error. And the EI, this is an estimation of the error. So if you write this as yi minus, in the book, the estimation of this regression line, this is the regression model, the linear regression model, can be considered as, according to the book, is b null having a subscript null plus b1 and xi. This is the estimation. So you can call this as residual. Yes, that's the residual. So in my case, this is the error, the random error, and this is the random error, and this one is the residual. That's the residual. Okay, let's speed up a little. The assumption, you can make all this reading yourself here. So I'm gonna move on to the next three items for the assumption underlie the sample linear model. For any given value of x, I mentioned in the beginning of the lecture, the y values are normally distributed with a mean that is on the regression line. So this is the one of the most significant assumptions. This is required for the linear regression model. Regardless of the value of x, the standard deviation of the distribution of y values about the regression line is the same. The assumption of equal standard deviation about the regression line is called homoscedasticity. If you're not satisfying the homoscedasticity, and it means you're having heteroscedasticity. This is in fact is not observed in ordinary variables. It is only observed when you have a time series data of x and y. So heteroscedasticity is common, and you cannot use the linear regression model. You cannot estimate. You shouldn't estimate in the ordinary way to get the linear regression model, and you can't use the linear regression model for estimation. So the third one is the y values are statistically independent of each other. For example, if a given value, if a given y value happens to exceed that mean, this does not affect the probability that the next y value observed will also exceed. So the y is a random variable, so it will change. It might exceed sometimes, it will be less. We will see all this in the following figure. This is a good figure telling you that this is the horizontal line x representing the independent, the explanatory variable or the regressor, and y is the independent or response variable in the linear regression model, the simple linear regression model. For a given x, this is the first value of x, this is fixed, you don't change it. So this is fixed, but the value of y may change from this to this place. So mostly if you have such x, and you will consider y between those two values, but it will vary from this line. And for a given value of the next value of x, a fixed value, it will also change. The y can change from, can take many continuous values. Okay, as I told you that this is the estimation of the linear regression line. Um, in practice, in many books, you may consider the estimated regression line to be y hat equals beta null. Beta null is the actual parameter of the intercept, but this is to represent that is the estimation. You have a hat. Hat is a representation of the estimation plus beta 1 hat and times x. So you may see such representation in many books. Okay, so don't forget about this. Okay, yes. So this is another representation. So I had the estimated value of the dependent variable, or sometimes you see that this is not estimation, the estimated value. You can call it as y hat is in many books in econometrics analysis. We call it predicted values. Predicted values. Value, okay. Beta null, the y-intercept, this is the value of y where the line intersect the y-axis whenever x equals null. Beta 1 is the slope of the regression line, x a value of the independent variable. Okay, the cap or the hat or the y indicates that it's an estimate of the unknown true value of y. The equation is completely described by the y-intercept beta null and the slope beta 1, which are the sample estimates of their population counterparts, beta null or beta 1, respectively. An infinite number of possible equations can be fitted to a given scatter diagram, and each equation will have a unique combination of values for beta null and beta 1, b null and b1. However, only one equation will be best fit as defined by the least square criterion we are going to use. So to estimate B1 and best estimate, to get the best estimate B null and B1, we use least square estimation. You can find so many, an infinite number of beta 1, B null and B1, but the one will be best fit. So we'll see with an example. So the least square criterion requires the sum of the square deviation between the original values of the dependent variable in the scatter diagram and the y values predicted by the equation be minimized. So it means we're minimizing that summation. So this is the aim of the ordinary least square estimation, is to minimize this counterpart. Okay, so all right, we have mentioned about the y hat. We're gonna move very quickly to an example to clarify. Okay, consider this example. Um, we have a regression line, this one and this one. So this regression line is, say, y hat, y cap equals 7 plus 2x. Okay, 7 plus 2x. Okay, and this line is 1 plus 3x. This is another estimation of we have 1, 2, 3, 4, 5 values of x and 5 values of y, and you're trying to fit a regression model or a line that's representing those five different combination of x and y values. Okay, to understand which line is fitting better, what we do is we're trying to square the distance. So this is a distance C, D, E, F, G. So you square this distance and this one and this one and this and this, and summing up the square, this distance becomes 100. It's given 100, and the one smaller, the one better. So the next one is the square of the distance according to this line. So this is 67. So in this case, I will consider this model is better fit. So this is how you conclude if you make a comparison between those two lines, and the next one is better. So you can never get the same square deviation or for different models, different simple linear regression model. It's only one. It should be a unique one. So it doesn't mean this one is the best fit, but this is better than this one. That's what I can tell. If I have the data set, if I use the ordinary least square, I will get the best fit. This is not guarantee. Okay. Okay, this is the way how you get the least square regression line having the slope. This is the slope. In my case, if I was lecturing within the classroom, I would write B1 as this one. Gonna change B1. In my case, B1, I prefer this one. Okay. The sum of x I yi minus the sum of xi, the sum of yi. This is divided by n, and I would have in the denominator part the sum of xi square minus the sum of xi square divided by n. This is my formula. I will prefer this one. It is identical to this one. No difference. In fact, they are identical. The reason why I'm not using this formula because okay, let's see. The reason why I'm not using really this formula is I don't want to get the calculation for x bar and y bar, the mean. I will have only the sum of x, the sum of y, and the sum of x. So here it's better for me, more practical. So as a result, I will also rewrite the beta b null, the estimation of the intercept. I wouldn't prefer to have the mean of y, so I will prefer to write the sum of yi divided by n, and b1 times the sum of xi divided by n. In my case, I prefer those formulas. Okay. Let's have an example. It will be better for us to understand how to estimate the regression line. A production manager, let me read you this example. A production manager has compared the dexterity test score of 5 assembly line employees with their hourly productivity. The data are in a data file, of course, and shown here. That's the data for fixed score x. We have those values. For if the employee A has a score 12 and the units he's producing in 1 hour, the first guy is 55 units he produced. And the next employee has a 14 score and producing 63, so it's increasing. And the next one is having higher score, even 17, and the units he produce is even higher, 67. And but sometimes the score from dexterity test is getting less, from 17 to 16 is a decrease in here, decrease. Um, but the units he produced even higher. Okay, for 11, so remember that for 12 we have 55. For 11 is decreasing the units. That's expected anyway. Okay, I'm gonna delete all this stuff here. Okay, so the estimation, if you use this formula, all you need to do to calculate xi, yi. So I can do it here easily. So I'm gonna use this space economically and delete all this stuff here. Okay, so I'm gonna have xi, yi in here. Xi, yi. So 12 times 55. So you need to multiply all this, and I use my calculator. Okay, let me see. 12 times. I'm gonna keep you wait for this. Okay, and I open my calculator. 12 times 55. This is 660. And the next one is 14 times 63 is 882. And 17 times 67 becomes 1139. And 16 times 70, 1120. And 11 times 51 becomes 561. Summing up, there's the sum of xi and yi. 561 plus 1120 plus 1139 plus 882 plus 660. Okay, the result is 4,362. So if you sum it up x, so this is 26, 33, 43, 49, 59, 60, and 70. And for this one, 55 plus 63 plus 67 plus 70 plus 51. And in total, this is 306. Okay. You also need to have xi square, yi square. The first one is 144, 196, 289, 256, and 121. You need to sum up all this also. This is 3025, the first one. And the second one is 63 square. This is 3,969. And 67 square is 4,489. 70 square is 4,900. And 51 square, one square, is 2,601. Okay. I won't lose time. I will read here, right here. So all this stuff that the sum of square of uh, xi square is 1006. This is 1006. Okay. And the sum of square of y 18 18,984. Okay, everything is okay. Yes, if you have all this stuff, substitute all this result within the formula of b1. um, you get the slope to be 3. That's the slope. Okay, I'm gonna have it within a box. Okay, and the intercept. So if you use his formula, because he has, the author has x bar and y bar, and use the formula of b null in this way. Okay, and you get simply the result to be 92.2. Okay. So the regression line, the least square regression line becomes y cap equals 19.2 plus 3 times x. Okay, right. All right. So that's the line. If you draw a picture of this graphical representation, it is good graphically. This graphic display is very good, showing that this is the value equivalent to 11, and this is equivalent to, for 11, remember the data, this is 11 becomes 51, so this will go to about here 51, and this is for 12, it goes 12 for 55, so somewhere in the middle. Okay, and this 14 I have for 14, the result for 14, let me see. 14, it is 63, so somewhere here. Let me draw all this stuff with a straight line to clarify. Okay. Okay. Uh, let's move it a little bit to right on 11. Simply, yes, the drawing is not very well performed according to the book. So if you draw this, it becomes like, okay, I'm gonna have it somewhere here. Yeah. So consider this as 51, and this one, okay, this is becomes to 12. So I'm gonna draw this, move it a little bit downward. Yes, okay. Yeah, this is just to show you that this is for 12. It's like, for 12 we have 55 for 12. So it's more or less, yes, the drawing is not very perfect anyway, but it is approximately, yes. And this is the best regression line estimation. So the distance, the square distance of this and this one is minimum. So this line is, in fact, is telling you that the square distance of the dot to the line is minimal. So I'm going to delete this. Okay. So this is how you can read this graphical display. You can use the regression line y hat equals 19.2 plus 3 times x. To estimate the units produced, any hour is not used within the data set. So if you consider that a person who is out of this range, who is not within this employee, say that, let's say he's producing a score 15. So 15 is not inside in here. So all you need to do to estimate the units produced for 1 hour, if his Dexter score is 15, you multiply 3 times by 15 in here, place 15 right here, becomes 45, and it becomes 60, y hat becomes 64.2. So it means the units he produced 1 hour is going to be 64.2. So this is an prediction. Yes, this is 15. 15 score. This is another person who scores 15, and it's not an employee within the data set. So this is 64.2 units an hour estimated productivity. That's very good. This is a computer solution using Minitab, and the book is giving you all this stuff for you. Okay. Um, I'm gonna just work out with these exercises for you, studying half an hour to come before I complete the lecture. I will study some of the exercises in here. Okay, the first one is explain each term in the linear regression model. So if you read the lecture notes, you will easily explain each term. So I will explain to you shortly. Yi is um, the value of dependent variable, the ith value of the dependent variable. Beta null is the intercept, the parameter intercept, or the constant term. Beta 1 is the slope coefficient of the regressor x, and this is a population parameter. Xi is the observation defects, the explanatory variable, the ith explanatory variable, and finally the epsilon I term is the error term. As I told you, it is not a residual. I wouldn't call it as a residual. In my case, this is only a random error. What assumption required? The second question is what assumptions are required in using linear regression model? Remember that we had 3 assumptions in the top of the lecture, in the beginning of the lecture. The assumptions for the first very significant assumption is yi should have a normal distribution. Yi should be distributed normal, having a certain mean, a certain variance, but it is normal. So n stands for normal. So this is the most significant assumption. And the second assumption is the epsilon I should have a fixed variance. So this is the second assumption. Remember, right here, it was called homoscedasticity. Remember, it is yes here, right here. So this is the second assumption. And the third one, remember that for any fixed value of x, and the yi is changing. So the third assumption, yi will have will vary according to different single x. So this is the third assumption. Okay, let's move on to the next question. In the linear regression equation, y hat is beta null plus beta 1 x. Y is the term at the left given as y hat instead of y. Okay, remember that this is beta 1 plus beta 1 x is the term used for the estimation. So this is, we cannot use the actual value of y. The actual value is only for this model. You don't use y hat or y cap for this model. This is the estimation. So this is a representation of the estimation. Okay, let's move on to the next question. What is the least square criterion and what does it have to do with obtaining a regression line for a given set of data? So the least square criterion is minimizing, remember the least square was the sum of yi minus y hat square. So minimize this, that's the least square criterion, minimization. Okay. So if you minimize this, you have a best fit. So this is why we use the least square estimation. Okay, the next question is, a scatter diagram includes the data points x equals 2, y equals 10, x equals 3, y equals 12, x equals 4, y equals 20, and x equals 5, y equals 16, and two regression lines are produced. Okay, two regression. One is y hat equals 10 plus 1 times x, and the second one is y hat equals 8 plus 2x. Okay, if you use the least square criterion, which of these regression lines is better fit to the data and why? So remember the those two regression lines. So all we need to do, we need to get the square difference, the distance, and calculate the square distance and see that which one is smaller. The smaller one is the better fit. All you need to do to check this. So to do that, it's simply I need to use a space probably somewhere here. Okay, I'm gonna try. Yeah, fine. Okay, I'm gonna try to use economically this space. For the first line, y hat 1 equals, for the first from the first equation, y hat value 10 plus x. The first value of x is 2, so it means 10 plus 2 becomes 12. So y2 hat, I'm not going to calculate that, it will be 10 plus 3 becomes 13, and the next one is y3 hat becomes 14, y hat 4 is 15. Let me see. Made a mistake probably. 10, 12, 13, 12, 13, 2, 14, and 15. Yes, 15. That's full. Okay. The square difference from the predicted value from the actual value, the square distance, is the actual value is 10. The first one is 10. The second one is 12. The third one is 20, and the fourth one is 16. So the square difference. So I'm gonna use this space economically. Gonna use this space here. So it will be, the first one is 12 and the actual value is 10. So it means 10 minus 12 square becomes 4. And the next one is 12 minus 13. The next one is 12 minus 13 square becomes 1. And the next one is 20 minus 14. 20 minus 14 square becomes 36. And the next one, the last one is 16 minus 15 square becomes 1. Summing up all this, so if you sum up all this value, 42. From this line, the first line, you get the sum of the sum of yi minus y hat square. Okay. I'm gonna use this one here. Okay, there is one. So this is yi minus y hat square. Okay, that's 42. Okay, this is from the first one. The first value is 42, and the second value, use 8 plus y hat 8 plus 2x. So from the second, y1 hat will be 8 plus 2 times 2. Okay, 2 here. See that this is 2, this is the first value, so y1 hat becomes 8 plus 2 times 2 becomes 12. Okay, y2 hat becomes, you're going to use the next value of x, which is 3, becomes 3, 6, 8 plus 6 is 14. y3 hat equals 8 plus 2 times 4, so it becomes 16. And the next one is becomes 8 plus becomes 5, 10, 18. Okay, so if you have all this calculation for the same things, and to make a comparison between this one and 42, so the first value is 10 minus 12 square comes 4, and the next one is 12 minus 14 square, this is also 4, and the next one is 16 minus sorry, this is not 16, 20, the actual value is 20 minus the predicted value is 16 square becomes 16, and the next value is 16 minus 18 square becomes 4. This is in total becomes 28. So since 28 is less than 42, the second model is better. That's your conclusion. Okay, this is simply done, this example, so we can move to the next one. Determine the least square regression line for the data in the previous exercise, 15.5 in here. Then calculate the sum of the square deviation between y and y hat. Okay, to obtain this, I need to have a space. Okay, there is a space in here, right here. So I'm gonna have the data copy this exercise, or maybe can write it immediately. So I'm gonna have this space in here, exercise 15.6. Okay, x, the value of x 2, 3, 4, and 5. Yi is given to be 10, 12, 20, 10, 12, 20. Let's see, the last one is 16. Okay, so 10, 12, 20, and 16 from here. See, 10, 12, 20, and 16. So I'm writing here right here. Okay, and I need the cross product multiplication. And this is 20. 2 times 10 is 20. This is 3 times 12 becomes 36. And this is 80. And that's 80 as well in total. This is 160, 180, 216. In my case, xi square, I need that. I need yi square. Xi square, 4, 9, 16, and 25. That's in total. This is 54. And this one is 100, 144, 400, and 256. So if you summing up all this, this is 400, 800, 900. Let me see, this is yes, 3, 4, 400, 800. Yes, that's not 900. Okay, everything is given, so I can move on to get B1. Remember the formula I was using here. I don't want to lose time. Copy the formula for you from here. Move it to the place I need. Copy this right here to the space I'm using here. Okay. Okay, right. So delete this, no need for this. Right. Let's see the result. All right. Okay, the sum of xi y 216 minus the sum of x. We missed those two. This is 10, 14, and this is 30, 42, 48, 58. Okay, so I need to multiply 14 by 58 divided by 4. The n is 4 in this case, and the next one is 54 minus 58 square divided by 4. Maybe I don't need this one. There's no need for this calculation because I'm not calculating the correlation coefficient. So maybe you can skip this. You don't need this anyway. Okay, B1. So B1 is becoming, I need to get this calculation done for you and see the result. B1 is 216 minus 14 times 58 divided by 58 by 4, and beneath we have 54 minus 58 square divided by 4. All right, the result is minus 0.165. Let me see again. Yes. Okay. Yes, that's right. 54 minus. I made a mistake. I'm really sorry. This is not the 58. I'm gonna fix this because I need to have 14 square. I'm gonna fix this. 14 square. So the result is delete this. The result is actually 2.6. So B this is B1. Okay. B null is, remember that the sum of yi divided by n minus b1 times the sum of xi divided by n. It's not that hard. 58 divided by 4 minus 2.6 times the sum of x, which is 14, divided by 4. All right, 58 divided by 4 minus 2.6 times 40 divided by 4. The result is 5.4. Okay, so the regression line, the estimated regression line y hat becomes 5.4 plus 2.6 times x. So this is the estimated, the least square estimation of the regression line in my case. So the previous estimation is different. So you have two estimation, y hat 10 plus x and y hat 8 plus 2 times x. Those are not the least square estimation. The least square estimation is this one. That's the best fit line. Let's see the square distance, whether the square distance is better. So I'm expecting, of course, the square different distance to be much better anyway. So y hat, I'm gonna have this place for y I hat. So for 2, if you substitute 2 within this regression line, the estimated regression line, and you get 2 times 2.6 becomes 5.2, and you have 5.4 becomes 10.6. The first value is 10.6, and the second one is having 3 here. 3 times becomes 7.8 in total. 13.2. Okay, and if you place 4, 4 times 2.6 plus 5.4, the result is, the next one is 15.8, and the last one is 5 times 2.6 becomes 18.4. Okay. 2.6 times 2 plus 5.4. 10.6. 3 times, yes, everything is fine, and I need to get this calculation done and check my model is better than the previous two models I had. This is okay. The first one is yi is 10 minus 10.6 square plus 12 minus 13.2 square plus 20 minus 15.8 square plus 16 minus 18.4 square. Okay, this is this it, and let's see, this is, I'm expecting this is even to be smaller than 28. 28, the second model was better, but our model will be even better because the square distance from the from the prediction will be smaller in this case. So let me calculate this for you. 10 minus 10.6 square plus 1.2 square plus 15, 4.2 square, yes, plus and 2.4 square. Okay, the result is in fact is 25.2. This is smaller than 28, smaller than the next one was 42. So this is 42. This is least square estimation. Estimated square distance, and this is from the second model. That one is the first model, from the first model. So our model is much better. The least square model is always better. So this is the best fit line, the regression line you can estimate for this data set. Okay, for pair of observation, the best fit line is this one. Okay, let's move on to be quick to the next question. I guess you can easily try to solve this question to which model is better. So you need to perform the same those two, and you need to get the y hat 1, y hat 2, and y hat 4, 1, 2, 3, and 4. You have four data, and you need to get the square distance from the first model and for the second model, and the smaller one is the better one. So this is how you conclude. Okay, maybe it is enough today, and we'll study some other exercises and move on to the last lecture in the next week, in the coming week. And this is the end of the lecture. I hope you enjoyed my teaching today, and take care of yourself and stay safe home. Stay safe home, and good night.